Okay, thank you, everyone. I'm Juan Gossen. I'm working at UMedSat. This is in Darmstadt, Germany, close to Frankfurt. So we mostly work with Sentinel-3 Olchi products, but as I'm working with in-situ validation, I started developing this tool for initially for Sentinel-3, but then yeah, perfect. So this ThoMas toolkit is developed to create matchups of biogeophysical in situ data with satellite ocean color products. Initially developed for Sentinel-3, as I was saying, the in situ data that you can feed into this toolkit is following the CBAS format. One of the specific ones, this one that each row is a different cast, let's say a different in situ acquisition time or station, however you call it, and the columns are, for example, the different wavelengths of RS. Of course, you need longitude, a timestamp, because that's how it will look into the corresponding satellite products. So initially, as I was saying, the UMedSat data store products, so Sentinel-3 Olchi, the operational ones were supported, and now we have NASA's OBPG products processed with L2Gen for some missions. So Maurice Aqua, some DIRS, and I also added Seahawk, this requested by the University of Georgia. And then now I've added pace in the last weeks, motivated by this hack week. So thanks for motivating this. So after running ThoMas, so ThoMas comes in different steps. The initial step is it transforms the in situ data that you have in the CBAS file to match the satellite in the sense of a spectral convolution or a band shifting. So spectrally and directionally, so a BRDF, to make it like fully normalized to the sun, looking at the zenith and the sensor pointing to nadir. So this is initially the first step with some, for example, unit conversion, whatever, to make it sort of a match whatever you have in this from the satellite data. Then the step satellite, let's say, will take the timestamps and the latitudes and longitudes from your in situ submission and go there. For example, for the moment, two possibilities are UMedSat data store for our products or NASA OBPG. So those that match the queries from your in situ, let's say, within a time tolerance, let's say, that you can define according to your matchup protocol. Typically, it's 1 hour, or it could be more if you are in more stable waters. Then the extractions. So this step is getting the satellite extractions according to your user-defined window, according to your protocol, and then getting the statistics of those extractions following this protocol. So getting the mean and standard deviation, flagging, removing outliers depending on what kind of protocol you're using. In the example of today, I understand you will be using the Bailey and Werdell 2006 protocol. And then there's a final step where the in situ component and the satellite are merged, and the statistics are calculated, and you get this kind of plots. I will show you later with a run done using PACE and a particular NRTOC station what you will. So the outputs are, so for each of the steps, there are several intermediate NetCDF4 files showing each of the intermediate results, because anything can fail at any time. Let's say, for example, you can have some internet issue, so you cannot get the full download of satellite data, or something in extraction. So each of the intermediate steps will sort of record and trace to each of the steps where something could be failing, or and also in the NetCDF4 format, this allows to store more specific, very detailed information, and then the CSVs of each step summarizing the most relevant information stored in NetCDF4. So these NetCDF4s are specific formats defined in this toolkit, let's say, like a matchup database, NetCDF4, or an extraction database containing only the satellite information. So, okay, I won't go into detail of all these steps because it's really long. So I just mentioned them. And we'll get some plots here, these other statistics, but then there are matchup by matchup plots with some RGBs I will show you in a while. So the motivation for having this is that it's well documented. So these steps are very documented, very well described in the README after a lot of revision from a lot of colleagues, and it's a good exercise for those going to the matchup exercise for the first time. So to go through this tool to see what are the standard practices in the community, maybe summarized here. So it's publicly available. So we had a lot of as we are dealing mostly with Sentinel-3, we have this validation team, and there's always the issue that different people show validation in these teams, in this team, using different protocols, and sometimes the differences in matchup protocols or decisions are sort of obscure because there's a lot of detail that one has to report. And the idea of this tool is to make it like open, let's say, to make it open to scrutiny, let's say, and okay, that's the idea. And it supports most of the commonly used matchup protocols in the community. These are some, the Humans Standard, the Bailey and Wardell, the CBORI 2009. We have one for systemic iris calibration, which is very stringent. And new matchup protocols can be easily added. And it contains a syntax to implement quality flags, combinations, and simple operations as flags that you can define. And it deals, and there's many assumptions with the propagation of uncertainties to the performance metrics. So, this is done using this Monte Carlo approach. So, okay, but this is still to be further developed. We have NPL Metrology Institute in the UK that will help us to develop more this part, but still coming. And then, supports many of the commonly used ocean color missions. As I was mentioning, Sentinel-3, MODIS, BIRS, Seahawk, and now PACE. It's depending on what kind of processor you're using, of course. It's a combination of processors and sensors that are being supported. And you can add new sensors with adding new configuration files. In the case of PACE, I had to tweak it to make the 3-dimensional RRS be able to be read, but it's already there. And it's just a baby, meaning that you have to be, of course, it's not going to solve all the issues of the matchup process. It's so garbage in, garbage out applies. So it's not checking for the quality of your in-situ data for the moment, unless you put some quality assurance flag. But it's still you have to be sure of what you are submitting as an in-situ input, of course. It does not deal with very very complex spatial temporal collocation criteria beyond the standards. So a maximum time tolerance window, a choice of a window size, some flagging, that there is nothing about, for example, spatial and temporal autocorrelation of the RRS. So this is still not dealt with ThoMas, and this is where NPL will help me, but it's still to come. So ThoMas cannot still compute matchup statistics of a set with varying extraction sizes. This is another thing that I would like to implement soon. And it does not, so the uncertainty assessment is still to be further expanded. But for example, it does not deal with intra-pixel variability, and it's not yet ingesting the pixel by pixel uncertainties that you have, for example, in the PACE products that I can see. So for the moment, the standard deviation of your macro pixels of your extraction window is the one that is taken as a first assessment of the uncertainty of the satellite component of the matchup. So yeah, this is still to be further developed. And so BRDF, the uncertainty of the BRDF step is not propagated, but you can apply both Morel 2002 and LEAD 2011. Those are the ones currently supported for both the in-situ component and the satellite component. And it does not do your atmospheric correction, okay? Just some people asked me sometime in the past. It's assuming that you have your product already atmospheric corrected and RRS is there, let's say. And many other disclaimers, but I hope it still proves useful. And many people just use it for downloading the concurrent satellite data. So maybe just the first step. So, okay, we will try to demonstrate the full workflow. So just some background on the matchups. This is the definition of the matchup according to ChatGPT. And you see that ocean color is listed as among other Earth observation parameters, let's say. So yeah, we need more than this. So just to mention that when we do the matchups, of course, we have to compare apples with apples. So we have to take care that what we are matching is actually matchable. And so we have to take care of a proper definition of RRS. So yeah, we use the RRS definition as in the Ocean Optics webbook. And so in general, what you would need to take care is about if you are actually reporting in your in-situ submission RRS, or maybe there is something that I don't know, maybe there is some difference in the definition there. And but okay, we use this definition. We and are this so for example, this is a scatter plot of the 400 band, but so we have to take care whether these are actually the same band, let's say. So if these are spectrally compatible. So for this, it has ThoMas deals with a band shifting approach to pair multispectral to multispectral and spectral convolution when you're submitting a hyperspectral in situ and you want to convolute to multispectral bands. So this was before PACE, okay? So I will show you what we have done for PACE in the next slide. And BRDF, so the directional compatibility, let's say, I put here Morel, but we also have Lee 2011 now supported. So this comes from a study by Dalimonte et al. That Lee gave us the scripts to do this. For PACE, we do the Talones Ibori Pitarch spectral reconstruction approach. This is before, so when I tried to apply the band shifting like I was doing for the multi-to-multi band shifting, this kind of thing happened. So the in-situ spectrum, which is the red one, had a lot of bumps, let's say, and this is because this band shifting of Melanan's clef, to accommodate for differences, is not well suited to match multispectral in-situ to hyperspectral, which is the case of PACE. So that's where I, with the help of James and also of Marco Talone and Giuseppe Sipori and Jaime, I added this approach, which is described in a paper released this year. And okay, I won't go into detail of this approach because I see that it's a bit late, but it's essentially based on hydride simulations and a reconstruction of a spectrum in a way that it coincides exactly in the multispectral bands, in the situ multispectral bands that are being reported, and then uses hydride simulations to sort of accommodate the intermediate bands to fully span the hyperspectral case grid, let's say. So this is an example of this is a PACE matchup. The RGB is flipped, so I already fixed that. But you see that the previous approach was showing a lot of spectral jams and was not well suited here. for the pace approach, you see that it's performing really well in this case. In general, above the 450 nanometers is starting to perform pretty well, at least for the Ethernet OC. This is just one matchup, but then we are typically for the moment getting a bit of underestimation in the 400, 450, and then a bit of negative reflectances in the UV. But okay, this is one example. So, and then about just to mention that there are different matchup protocols, as I was saying. So we have to take a decision here. I guess I understand that there you will run an example with Bailey and Werdell. So I will skip the UMETSAT one, and we go directly to the Bailey and Werdell. So in this case, I'm setting a 5x5 window. Maybe this could change according to your site. It could be 3x3. And there is a first step in which of your satellite window, some pixels are flagged. So your protocol has some quality flags. And then from that set, you remove those pixels. If less than 50% of the pixels have survived this, then the matchup is discarded. So the extraction is discarded. And then there is an outlier detection. And so some going outside of let's say, the histogram of the macro pixel, those are discarded. And then there is this screening according to the coefficient of variation of RRS and AOT. If it's larger than 15% in this particular matchup protocol, then the window is discarded. But assume that these two red criteria are well met, then we have a final window without outliers and the flag pixels, and then the median is taken as a central value, as the reported value, and let's say an uncertainty measure of type A. I don't know, it's type A, I think I made a mistake there. It's a standard deviation, and a coefficient of variation as a homogeneity measure of the RRS. Okay, so this is just to illustrate the importance of the impact that choosing different matchup protocols has on the results. This is from Concha et al. 2021, but I will skip this. So the message is yes, the matchup protocol that you choose has an impact on your results, on your matchup performance metrics. And so this is a summary. Oh, I'm very late. Sorry. Okay. Just tell me I should stop, and I just stop. So these are just a summary of the performance metrics that we use, that are reported after ThoMas is run. These are mean differences, either percentual or non-percentual or absolute, or let's say all these possible combinations, which are comparing the satellite and the in-situ sources. And then we have the log-based, let's say, transformed, following a recommendation by Bridget Seegers. Then we have the median equivalent of this, to which some people prefer because they are more robust under the presence of outliers. And some spectral statistics, such as a spectral angle mapper. So this is a unique number for the whole set, because it takes all the bands, and it's sort of measuring the angle, let's say, between the two sets, the in-situ and the satellite, and a chi-square. And there are linear regressions of two types, so least squares and the tail sen, which is more robust under the presence of outliers. I will show very fast. I think this is the example that you will run. Actually, I'm sure about this because we checked a while ago. But this is with the Casablanca platform. This is an Ethernet OC station in this region of oil drilling stations. This is the southeast. Sorry, I said it the other way. Southeast of Spain. And this is a multispectral instrument, Ethernet OC. And I will maybe, I am just putting here an example of how it would run. So in this example that you will run in a while, we test this particular RNA-OC station during March to July 2024. In this case, in this example, ThoMas will download the RNA-OC from the official RNA-OC website and will transform to the CBAS format so that it can be fed to the whole ThoMas workflow. And then I tested the workflow with NOAA VIRS and PACE in the same time range, with the operational collection that is available there in OVPG, and using the extraction protocol of Bailey and Wardell with an extraction window of 3x3 and a maximum in situ satellite time difference of 1 hour. And then I skipped that. But in this case, I'm applying the Morel BRDF, and I only keeping the closest in situ acquisition to the satellite overpass. Okay, so typically ThoMas runs with these configuration files. So you set each of the steps that I was mentioning, and you set the parameters. It is a bit complicated if you see it like this. There is a lot of information, but okay, we have now a GUI which is operational, let's say, since today, and I wanted to show you very fast that. Okay, so to run ThoMas, you need in your case, it's an OVPG credential, so your Earth data, user, and password stored in a hidden file that is documented in the README. Forget about the step 2. So you need to clone the code, of course, and to set the conda environment and set your configuration file. Okay, so this sort of file that is shown here with the different steps. And the input in situ file, you will get it in this example from RNA-OC. So this ThoMas will create it. And once you have all this, which is a lot, you run the main.py, so the main script of ThoMas pointing to the configuration file. So this is a way to run it with a command line. But now we have a GUI, and so the GUI simply runs. Just a second. The GUI simply runs by calling the main.py function. I'm already with the conda activated here in ThoMas, and I'm in the ThoMas repository, which was previously called ADB. And so you're seeing the GUI there? Great. So maybe in this case, the GUI sort of defines each of these parameters that can be run from the command line. So I think there's no more time, but you can test with this. I just so the kind of results that you would get at the final once ThoMas finishes is this NetCDS and CSVs and PNGs, and you get these kind of things, right? First, the matchup by matchup results. So this is VIRS. This is one matchup. This is the closest in time matchup for PACE. So this is the same in situ, but you see, so the red spectrum is in situ, and the blue is the median of the extraction window with this shade of cyan. I don't know how to call it. These are the individual pixels of the extraction window. And you see, of course, here the in situ is convoluted or band shifted to the VIRS bands, which are few here, and this is the case of PACE. Okay, which is a lot there, and it's matching pretty nice in this region of the spectrum as far as all the tests that I have run. And then you get this kind of scatter plots. So for example, this is 490 band with all the statistics that I was mentioning and a bit more. And then you get for example, all the satellite versus in situ, in this case for NOAA, the right for PACE, and you get this kind of the differences. So this performance metrics with this shade is assessment of the uncertainty propagated to these performance metrics. And these are median difference, median absolute difference for NOAA and PACE. So you see that they show very similar, which is a good symptom, let's say, that they are showing this very, very similar, because we are using the same matchup set, let's say. I mean, and these are the percentage differences. Absolute in the case of the red, and violet it's the non-absolute, let's say, and let's say the signed one. So yeah, so these are the prerequisites. So the Python kind of packages. This is done via Conda environment. So this is a summary of the human metadata store, credentials, and NASA VPG. Everything is there in the README of the repository. Forget about the ECMWF for the moment. So this 5 and 6 we can skip. And then to get the code, you need to clone it. Maybe with this depth 1, you avoid cloning all the commits. So this will be much lighter. And remember to update it, because I've made some recent changes today. So git pull origin main. And this is how to create the environment. So from the environment YAML file that is there in the repository. Sorry that I went very quick. This is the last slide. So is there any question? It's welcome. Thanks.
Thank you.
Any questions from Juan? I'm going to show you a notebook. So he explained how you can run ThoMas command line. He showed you the GUI. I'm going to show you very quickly the notebook where you can run ThoMas. But before that, any questions for Juan?
No, I can only hear Anna.
I'll repeat the question. Go ahead.
In the comparison of PACE with AeroNet UC is multispectral. So was it converted to hyperspectral using coherence method and then compared with PACE OCR?
Question about AeroNet multispectral data convolved to hyperspectral data, how that was done, and is that how was that done?
So I'm still sharing my screen, right?
Yeah, you are.
Great. So yeah, I went very quickly through that because I was in a hurry. But so this is the method that Marco Talone, Giuseppe Cibordi, and Jaime Pitarch proposed for validating hyperspectral arrays using AeroNet OC. So this relies on a hydrolate data set. So, for example, when trying to validate multispectral, for example, let's say Olchi with AeroNet OC, there's also some spectral matching that needs to be performed. And in that case, it's Melan and Sklep. Okay. So that's very easy because typically the difference in wavelengths is very small. And then it's just a QAA inversion. So this quasi-analytical approach to invert, and the correction factors are very small. In this case, because the spectral distances are a bit larger, because we have only a few bands and then space has a lot, let's say. So this is why they decided to go for hydrolite. And what they do is, given the multispectral in situ input, they find the 3 closest in this reference data set of hydrolite simulations. And then they, let's say, they do like a blending of those in a way that the bands, the multispectral bands, so the original input bands are so the output spectrum is coincidental in those originally inputted, let's say, to the algorithm. So yeah, that's what we have. of course, this is, they have shown that it's pretty, so they have validated this with some concurrent hyperspectral in situ, and they show differences typically less than 5%, but of course, this is, I mean, it's what we have for the, we have multispectral in situ, but we need to validate hyperspectral. This is some sort of way to circumvent the issue that we have a lot of missing information in situ, right? Yeah, otherwise we would go for hyperspectral in situ, of course.
Thanks, Juan. Yeah, I was thinking of your group when he showed this slide, because they're trying to maybe fuse Landsat Sentinel-2 multispectral data, so I was going to recommend read this paper. So glad you asked. Okay, any other questions for Juan? Okay, I'm going to share my screen, Juan, so you can follow along. The ThoMas notebook is on the website, matchups of in-situ data with satellite data ThoMas. You can download that, pull it into CryoCloud like we did yesterday. This is what it, nope, that's not what it looks like. This is what it looks like. I'll just show it here. So this notebook was modified from a Copernicus Marine Training Service Jupyter notebook developed by Juan and Ben Loveday and Haley Eversking from UMetSat. So it just gives a summary of ThoMas again, the learning objectives, how to set it up. We have the newest version of ThoMas shared under the shared PACE Hack Week 2024 folder. So this notebook will work with that cloned repo. It's already saved in there, so you don't have to do it. You do have to save this credentials file that Juan was talking about. So you have to make a JSON file with your Earth data username and password, just like this, for it to run. And then this is creating the config file for ThoMas. We're using the Casablanca platform, AeroNet OC site. There's a little function here to write the config file. You save it in a new output, and then this is how it makes it. So you put in, the dates that you want to run, which AeroNet OC, what AeroNet OC level data, the BRDF protocol, the matchup protocol we have down here is Bailey and Wardell. So you fill this out. This saves as a config file in your directory, and then you can run it, and it goes through and it downloads all of the AeroNet OC data. It downloads all of the PACE data. It can take a while if you're doing a long time range. I think this was March to July. It took probably 30 minutes for it to run completely. And then at the end, in the directory, the Casablanca folder that will save in your CryoCloud, it will have matchup plots, it'll have all the statistics, it'll have a net CDF of the matchups, like Juan was saying. So we're not gonna, we won't run through this notebook, but if it's there for you guys to take a look at and for future reference. What's also there is another notebook just called Matchups of In-Situ Data with Satellite Data. That one we're going to talk about now. So you can either look at it here or download it, pull it in. I'm going to open it up in CryoCloud. So I have it already here. So this notebook's very similar, but it's using functions that James has developed to do matchups. So quick summary. We're still conducting matchups of the AeroNet OC Casablanca platform and PACE RS data. Little information about the platform. So at the end of this notebook, you'll know how to access RS data from an AeroNet OC site, how to access PACE OCI RS data from a specific location and time, match those data up, and apply statistics and plot matchup data. I don't know why. Okay. And I'm going to turn it over to James now because he did most of the work for this notebook. I just put it in a notebook, really. So he'll explain his helper functions and then, and then show some results that we already have plotted.
Yeah.
Yeah, go ahead.
So, hey, I'm James Allen. I'm here for in-person today. I'm going to try to see if I can help out throughout the week, but if I'm not here for the rest of the week in person, you still have my email, so feel free to email me, ask me any questions you need, see if we can get things going for your projects. So in that regard, I tried to set up this notebook in a way that made it just super copy-pastable. So whatever you need to do this, take whatever you need from it, copy paste it into your own notebooks, tweak it a little bit to make it work for your data, and then see where you can go for it. So the way I have this set up, I just have everything dumped into this one setup cell. And so I have all these imports, these helper functions, and then I set up just a couple of the dictionaries for limiting you to whichever ARINET sites that you want to set up. I have a little bit of column changes that I have to do to make things work and make some plots pretty colorful, not as good as Karina's, but I'm trying. And then because I'm lazy, I throw everything into a dictionary and just say, hey, I want PACE. Okay, now I don't need to remember that I'm taking PACE OCI L2 AOP NRT. I'm just going to throw it in here and say, give me PACE instead. So based on all of the things that Juan really covered a lot of, and I'm going to just defer to the fact that he's covered a bunch of this already, I have this split up into basically a general utilities section. This is where you get that F0 parameter, the solar irradiance at the top of the atmosphere, so you can normalize your data from the field, do some bandpass averaging, get some columns. This is basically just data set manipulation. And then I have it set up into, here's the utilities that you'll need for ARINET or your in-situ data of choice. And then here's the utilities that you're going to need for your satellite data. And so for the satellite utilities, I definitely heavily use Earth Access to pull everything and kind of manipulate it and store it into these. I was lazy and just shoved it into pandas flat files because I just wanted to have a nice little remote sensing spectra matchup one-to-one for each thing. But there are much more elegant ways to do things in NetCDF files and things like that. So if you wanted to talk to Ian et al. To figure that out, that's a really good way to do things too. And so each of these is set up. I have a couple of subset utility functions and then process satellite or process ARINET. And those are the things that just kind of run all those utilities so you can have a nice little clean, I want to process satellite when you run the notebook down below. And so moving on to down below, I also made some plotting utilities. This is kind of really similar to what we're going to actually do for the PACE OCI validation metrics on the OBPG website or whichever website we're posting it to, PACE website. And what these do is, I'll go over this a little bit more, but it makes, instead of just doing scatter plots in log space, because I like hiding all of my statistics in there, I try to put it into bias versus paired means so that we can actually pull out and see how is this actually performing. Fun fact, it will really make your data look bad if it doesn't match up really well. So it's really mean to your data as you do matchups, which is what we want. We want to know where we're performing well and where we can work on things a little bit better. So after this convoluted mess of a script that you can get through in cell 1, you can hide that by pushing the blue bar over here. It'll make everything all nice and pretty. And now we're just looking at the notebook as it is. So it's all hidden in this little thing over here. So the first section that we're doing is just processing the ARINET data. So the way this works is it's going to build a little URL script that can just be posted, and then we use requests to pull that data as a flat file from the website, and then just store it in this nice little flat file that we can have, what platform am I using? What's the date time of the measurement? My lat long, solar zenith, and then the remote sensing reflectances that we're doing. And then if you wanted to break into the things, and you can kind of pull out, oh, maybe I don't want this water leaving radiance, maybe I want this BRDF corrected water leaving radiance. And you can kind of switch things around there and make it fine-tuned to what you're wanting to look at for your satellite matchup data. And then the next section is the process PACE OCI data. And so this is basically going to pull all the lat longs that you've made and all the different time points of the data that you were actually able to download from the website, and then do a manual search through it and just pull the OCI data using Earth Access for those time points and download those. It's still quite slow. The fact that you're on CryoCloud will make this a lot nicer, but if you're just pulling it onto your local machine, it is going to do the cloud to local part, and it makes it take quite a while. But it still works. I think it took me an hour and a half, what it took you 30 minutes to do, so it still works, but it'll get the job done. And so after it does all the granule checks and everything like that, we ran it from March 1st through last week and got all these different time points. And then I have this shove all the data together. And this is where what Juan was going over with the Bailey and Wardell criteria or the UMETSAT criteria. What this does, I did a little question mark match data so you can see what my inputs are and what does it actually mean to have CV max or SINZ max. And so this is using the coefficient of variance criteria of 0.15. Basically, that means that your signal to noise ratio needs to be 6 or higher. As long as you have your data is 6 times higher than your standard deviations, that's considered a good matchup point, so we'll use that. We also do some sensor zeniths. If it's too far down close to the horizon, it's probably not going to give you the best matchup data, so we should at least bump it up to a little bit more closer to nadir. The 5x5 pixel is what I'm stuck with right now. We can switch it to do 3x3 like what Juan was doing with his version of the Casablanca platform. But after we have those 25 pixels, as long as over half of them are valid, i.e. the flags for L2 did not trigger it to say that this is not a good validation pixel, then okay, this is going to be a good matchup for the criteria that we're doing. And then I set mine, instead of 1 hour, I set mine to 180 minutes, so 3 hours, because I wanted to pull as much as I could to make these plots look kind of gross, because I want to see what they look like, just to see what happens for it. And then after we do all those validation pixel pulls, we basically toss out anything that's more than a standard deviation and a half, and then use the means and medians of the leftovers. And that's what I call a validation plot. So you can make this as strict or as loose as you want to call it a validation matchup point. And so after doing all those fun things, for March through now, we have a grand total of 31 matchups. And so I do a little bit more cleanup here. I just basically pull the products because it's hard for me to just specifically say, oh, I want to match up AOC underscore RRS 400. I'm lazy, I just want to type 400 and say, here it is. So after I do those and pull out those columns here, I now finally get to the bland Altman plots. And so this is what I was talking about earlier, where we're basically plotting the biases as a function of the paired means. And so this is what really pulls out all of those variations and things that we were looking into to see whether a pixel is considered validated or a good matchup, or the data is actually doing what we expect based on the observation measurements from the ground. And so I have a couple of defaults set up for y'all. You can just run it as is and throw in your X's and Y's, and it'll take the rest of it just as is, do a type 2 regression for you, and then make these plots. And so what these are now, and this is gross. I'm just going to let you know that now. But from our 31 points, we do see that there is I do a regression check against it to where I try to see if, as a function of the magnitude of the observations between the satellite and the field, do my biases get bigger or smaller when I go to one end of the spectrum versus the other? And that tells me that I am biased, I am dependent on the scale of the data. So if I have high biomass waters with nice big chlorophyll values, I'm going to see a bigger bias than I would in the blue oligotrophic seas. And this is a good criteria to check, oh, maybe there's something that I need to do to call this a better matchup for in the future reference. And these are, I mean, I'm not going to mince words. These are just gross matchups because we're pulling one station. The algorithms that we're doing for OCI are built for the global ocean. And when I do pull all 30 stations that I have for the AirNet OC matchups, it looks fantastic. But we're focused on one tiny little region where we have regional chlorophyll algorithms that probably work better than the global OCX algorithm that we're using. So this will be a little bit noisier than what we would expect to see on an actual true validation matchup. So that's why the graphs look like this. And you can see it does put out a whole bunch of stats for you. I've made it to where if you wanted to pull the data frame of your statistics matchups, you can just pull all that and use it in your processor of choice, your grapher of choice, and say, hey, this is where I'm doing it. I'm having this kind of bias in these kinds of regions. This is what I want to see and explore for future projects. And so this is kind of like the trial by fire. I'm actually kind of impressed at how well it did for one platform. So this is actually really nice. And so when we do not have this scaled dependence based on the measurements, the observations and the biases based on the magnitudes, it does put out what we call the limits of agreement. And so what this is I'm going to take the variability in the field measurements and then basically set that and say, hey, are my OCI observations within the field variability? And if they are, awesome. That means that I'm actually doing something really nice, and I can consider myself in agreement with the field data because I'm within the field variability. I can be wherever I want in there. As long as I'm within that, I'm considered a good matchup point, or a validated point that the satellite and the field agree with each other. So this is me blasting through, but I can go into more detail. I just wanted to make sure that I covered and explained what these plots were showing. Because, I mean, you know, scatter plots are great and all, but it really doesn't show very much when you have all these different kinds of metrics that you want to pull out. And so Bland-Altman plots will really like air the dirty laundry of statistics for you. So that's why I like them a lot more. But that's my trial by fire. Sorry for the fire hose of information, but feel free to copy paste and use to your heart's content.
Any questions for James? Or Juan? I think he's still on.
Juan, you still there?
I'm still here, but I'm leaving soon.
Oh, okay. It's like
a bit late
6 hours from now.
Just to mention before I leave, thanks, James, that if you're having any trouble with ThoMas, you can always send me an email. These days in the office are very quiet, so everyone is on holiday. So you can always email me if there is any issue and you are trying with ThoMas. Okay?
Cool. Thank you, Juan, so much.
Thanks. Ciao, ciao.
Bye.
Ciao.
I guess I have a question really quick.
Go for it.
If someone has chlorophyll data or another parameter, can we use your code or modify your code to do chlorophyll matchups?
Yes. So the way that you would do that is for the OCI part, you would just switch that, pull the level 2 AOP NRT, switch to the product that gives you the chlorophyll values. And then for your field data, you're going to have to just delete most of the ARINET code, but use the parts where you can pull a latitude, a longitude, and a time point of your observation. And it should be able to pull the Earth access point for the satellite part that matches that time point for you. And if you have a lot of different time points across a bunch of different areas, be warned it will pull a satellite value for each of those, and it takes a while, like at least 45 seconds per point if they're not all clustered together. So with that note, you can do any kind of matchup as long as you have the coordinates and the time points for it. Yes?
Can you talk a little bit about that matchup section? So you're going through it. It sounded as if like that your code is, you know, it has the point and it's somehow making some decisions about what is the best matchup point. I didn't quite follow that.
Yeah, that's a great question. So what this does is I have a data frame for my satellite data, and I have a data frame for my in-situ data. And what this does is based on some criteria, based on the Bailey and Wardell 2005, those are the default values, or 2006, these are the default values that come in here. So it checks against the maximum coefficient of variation, so your standard deviation divided by your mean, and make sure that that's no greater than 0.15. It checks against the solar zenith angle for the satellite data, so anything that is like greater than 60 degrees as the default, it's going to say that that's not a valid pixel, so it'll just say this is already being tossed out as a validation matchup point. It checks for the 5x5 extractions for the satellites and make sure that you have at least half of them are valid based on the level 2 flags that we have for OCI. And then that you're in the field data, your time difference between the satellite matchup point and your field is no more than 3 hours away from it. And I think also if you have multiple matchups, so I have one satellite overpass and maybe 3 hours worth of field data, they're all considered valid because they pass these metrics. I'm going to take the mean and standard deviation of them, toss anything more than a standard deviation and a half away, and then take that mean, and that's going to be my matchup point. So this is kind of like making sure that I have one valid field point that is covering that time band that I've allowed it to be for the satellite. And so these decisions are being made in this script, and I've hopefully coded it enough to where you can say, oh, I'm filtering it based on these metrics, and then eventually it'll just say, hey, did all of these matchups work? Okay, now put it out and then store it in your data frame of your matchups. And so it'll put satellites next to field data all on one row for you. Does that hopefully answer your question?
Yeah, I'm trying to think about this and like if you were trying to do matchups with like level 3 data.
Yes.
And I guess I'm not familiar enough with the level 3 data to know if all of those would be present. It almost sounds to me like a lower level.
It's more of a level 1, level 2 level, because 3 is bend based on a bunch of different metrics. Like we might have 8-day bends or daily bend. Well, dailies would work, but if you're merging a whole bunch of big pixels together, you might have a lot more variation. If you can find a way to pull out the standard deviations in the bend data, so if you use level 3 bend, you can kind of pull out more stats. You would be able to work it into these kinds of scripts. I think there's probably more elegant ways to do that, but that would be the way that I would tackle that, is get the uncertainty metrics for the level 3s that you're pulling, and then let that dictate whether you call this a good validation metric or not. Does that answer?
I was going to say, some of that screening's already been done in the level, when you're averaging into level 3, you're throwing out
Oh yeah, because
flags and the flag data and stuff. So.
it's not masked, it's actually flagged out.
Right, okay.
Yeah.
So along those lines, that the statistics, the CV that is the CV of what?
It's what's the best way to explain that? So in my 5x5 grid of satellite pixels, I calculate the mean and standard deviation of it. If the standard deviation of that is just all over the place, I'm going to say, no, I'm not even going to try this. Yeah.
Got it. So there's too much variability within the 5x5 extractor.
Yes, and that's because we either have like edge effects of clouds or things like that, all kinds
So
of.
my question is, can you change the size of the extraction array? Could you do a 3x3?
Yes, with some coding. I have it just brute force set to this. If you wanted to change that, it would be up in the satellite spot. There's the get 5x5 code. And
That's
yeah.
what it is the get part.
Yeah, the get 5x5, and then I have the indices for the 5x5 box, just -2, +2, -2. Just change that to 1, and you're good.
Can that script pull from a level 3?
Yes, this can, yeah. This will work on level 3.
So that would be how you could find, that's how you could.
Yeah, it finds based on your field data, the lat longs for it,
Yep.
gets the Euclidean distances and finds, oh, this is my pixel matchup. And then you just do +2, -2 for the 5x5 or +1, -1, yeah.
I have some other matchups that I need to do, like with SST and some other products, and so we were trying to figure some of this stuff out.
Oh yeah.
This is very helpful.
I mean, you can also make it just, I want the closest pixel, but good luck.
I do want to do my rebuild.
Yeah.
But I work in a much more dynamic area, so I tend to do a 3x3 instead of a 5x5.
Yeah, there are conversations happening on whether we should start switching from 5x5 to 3x3, depending on which
Really open
waters we are.
matter as much, but
Yeah. But these coastal AirNet stations where they're all like on oil platforms just off, I'm like, well, okay.